Okay, thank you for invitation. It's very nice to be here all together. I remember old times. We met in Bavaria or in other places, but now we met here in Latvia. And of course, I would like to introduce myself. I'm Grazina Skridlaite from Nature Research Center in Lithuania. It's a kind of a scientific institute. And I made it together with my colleague, Laurina Šilauskas. But of course, I want to thank all colleagues from Sweden, Finland, Poland, Estonia, Belgium, and well, many, many other countries who actually helped with data, with advertising, and with a lot of other things to improve our scientific career. Of course, I start like everybody did with kind of history. Because when we regained independence, like we started a new science, because everything we knew it was okay. In some things, like in mineralogy, we were really excellent, petrography, but in some other things, we didn't know anything. Can you imagine in former Soviet Union, plate tectonics were not taught at all? I mean, you had to start many things from a beginning. And we started to collaborate with Western colleagues. We invented some special projects and grants. And one of this, I would say, major international project was Eurobridge. Eurobridge, well, it was a really huge project for several years. It continued for several years. And many seismologists from all over the world, they came to Lithuania, and of course they started in Sweden, the Baltic Sea, in Lithuania, in Belarus, and continued to the Ukraine. And we, first of all, obtained deep structures. Of course, it was this profile, but data was a bit old-fashioned, and now we got new data. And one of the most important subdivisions, like in the central Lithuania, was like a jam between depth of crust. It was like in one part it was 44 and in another it was 55. And we thought that it's kind of a major structure. And based on that idea, we compiled some maps. Like one of the first maps, it was for Eurobridge, made for Eurobridge volume, for tectonophysics. It was just featuring like in a central Lithuania, with the middle Lithuania, like huge zone. We thought that two different plates came together and we had some subduction and what's on. Of course, later on it turned on that nothing happened like that. But many maps actually were based on that idea, and some later maps were produced, like by Gediminas Motuza, colorful, very detailed maps based on different approaches. But when we analyzed those maps and when we started to get isotope data, like proper geochemistry and all other things, it turned out that they don't work. This is more detailed map of southern Lithuania. And as I said, when we started to acquire real data on isotopes and to make some kind of tectonic interpretations, it didn't work. Actually, we didn't find rocks which were on the maps, and we got totally different rocks, and ages didn't match. And of course, none of those sketch maps, as I said, were proper maps. They didn't work for, like, say, modern tectonic interpretations. Like lithology approximations were not enough, because we have different lithologies. Can you imagine you have granites, like now we have in Lithuania, of 7 different ages. And they come to the contact in the same place. What you saw on map, just granites, but they produce totally in different tectonic regimes, and they bear different information, different mineral resources or whatsoever. And of course, the lithology and geochemistry, it's not enough for proper maps of crystalline basement. Of course, and geophysics to compile it with geophysics. And then we needed a proper map and proper model. And luckily, I went to Sweden, and so I spent quite a lot of time in Sweden at Lund University, and we worked together with Svetlana Bogdanova. And Svetlana Bogdanova, unfortunately, already deceased, like in Roland Gorbachev. She had a huge pile of data on all geology and geophysics of all Baltic countries. If you imagine, she had like shelves filled up with files on Estonian data, on Latvian data, and on Lithuanian data, all the published, all paper maps and everything. And we checked carefully, I would say for years and years, for 5 or 6 years, we checked all the data. And then we decided, oh, we have to have some new concept based on orogenic cycles. And just to do kind of a structure, like tectonic structure, and then to fill in. And then this map you already saw in many cases, I will show a bit further. And what it was based on, because some people who do not believe this map, actually, I try to convince, but it's a really good map because it's based on a huge pile of new zircon ages. I mean, we dated, like we chose some area, like empty areas, of course, not Latvia, because we had no samples at the time. And we dated some rocks. We dated some rocks, additional rocks from Estonia, from Lithuania. I myself dated Valgo and Kernel from Estonia because I went to Nordsim facility in Stockholm. And we really supplemented the data with the new. And then we got, as you see, a lot of new age, like real proper age data. And we used all our PC, all metamorphic data, all geochemistry and geophysics. And of course, we did kind of a map. Of course, Svetlana was the first and Roland helped, but we worked quite a lot because I myself was involved, as I said, for 5-6 years. And you see here on this geophysical map, it's kind of a background. It's a map by Polish geophysicist Krolikowski. And we used this map like a background for major structures, like just showing some boundaries and drawing some boundaries and some major like shear zones and something. And on the right side, you see the map we produced. Like already Alvar showed and many other people, in Lithuania you have something like subdivision Mid-Lithuanian domain, West Lithuanian granulites, and Latvian East Lithuanian belt, which is very similar with Latvia. I think most of Latvian geology is fits this interpretation. And of course, we go to Estonia, and in Estonia, we have something similar again with Eastern Lithuania. Like, well, okay, we have to compare. We have a lot of data together with Latvia and Estonia, and Mid-Lithuanian domain and West Lithuanian granulates are slightly different, slightly younger. And this is compilation of all ages. Svetlana did. These are not only ages from Baltic states, but also from Sweden, Finland, and from other countries. And you see the perfect fit, like Bergslagen fits South Estonian and Latvian, East Lithuanian, and Mid-Lithuanian goes a bit younger. And well, it confirms the idea of younging accretion towards the south, actually introduced by many of Finnish geologists and geophysicists and Swedish. And actually it proves like that because we have all the units in Estonia, slightly in Latvia younger, and then it's younging towards in Lithuania, in southern Lithuania, western Lithuania, and of course in Poland. And Polish people proved it because they have only much younger data. And then this model was reconstructed based on data, like a bigger model, correlating some units with units in Sweden and in Poland, and of course in Finland. And you see it's quite, well, I would say it's kind of approximation to the sketch map, but fit is quite well. And we still had not enough data. What we started to do next, okay, now we have to choose key areas, because you know in crystalline basement you can't date all rocks, you can't estimate on rocks. You have to choose key areas to solve some key problem. If you solve it in one place, you can extrapolate to other places. And we started to do with this Mid-Lithuanian domain, which was a little bit younger than well. And we started to acquire additional data. We had some data already from uranium lead, from Nordsim mostly. And then we got data of samarium niobium and strontium rubidium, thanks to Åke Johansson from Stockholm. And we compiled this data, and you see on epsilon niobium and of course all other contents, but it fits very well with mafic Lithuanian rocks in East Central Sweden. I mean, and second thing, what was very important for us, and I advised to use rubidium strontium and samarium neodymium, because we got a series. You see all our data. This is a data from southeastern Middle Lithuanian belt, and this is from northwestern part. But it's aligned. All data is aligned from different rocks. These are gabbros, diorites, granodiorites, granites, slightly metamorphosed. In some cases, even metamorphosed in granulite facies. But you still can recognize, and it means when you put, and here especially initial strontium, it shows that actually the source was the same. They originated from the same mantle source. It means you have perfect fractional crystallization series. You can align, just assign all these rocks to the same complex. It means it's very nice. You don't have to, just draw many, many colorful patches. You just can draw a complex, which consists of diorite, of gabbros, diorites, granodiorites, and diorites. It means it's much easier because you have already like a structural boundaries, and you can deal within the structure with some details. And of course, what else we did? We did relief elements and of course pide diagrams, and you see all of them are really perfectly aligned as it should be. Of course, mantle source was slightly different. I mean, if you deal with volcanic arcs or continental margins, you know that mantle is not uniform beneath that. And we used HARC diagrams. HARC diagrams, again, are very good to check if the series, if rocks belong to the same like igneous series, magmatic series. You just see again perfect alignment. Just CO2 changing, it means you have all these gabbros, diorites, granites again aligned on the same line, and you see that they fractionated from the same mantle source. And then we compiled all the data we had from uranium lead, and of course you see again with new data and old data, they fit very well. And of course we had younger, and all these data are just in a range of 187, 182. And they cross-cut by younger rocks, younger chernokites, younger granites of 181 and 180. Actually, it's the same like in Sweden. And as I said, we subdivided this Middle Lithuanian domain already into two parts, like northern part and southeastern part. And you see on the picture that we can correlate these complexes with the complexes in Sweden. And of course, it's a very good fit, first of all. And second, as I said, it's like southeastern Lithuanian mid-Lithuanian part of this domain. It's more like a volcanic island arc complex, and northwestern part, it's more like continental arcs. Again, and we were very lucky because at similar time, Yevgenia Salin from Tartu University defended her thesis, and she published a couple of articles, and she recognized, or based on other approaches, that in Sweden they recognized so-called TIB 0, Trans-Scandinavian Igneous Belt 0. It means it's exactly of the same age as we got for our Lithuanian belt. It means, well, again, it proved that our interpretations are really fit, and they are good, and we can now just prolong through the Baltic Sea and continue towards Sweden. And then another key area, of course, Latvian East Lithuanian belt, which is really complex, because you know Svekofenian is not so simple. It's much more complicated. And we dated quite many rocks. We started actually like to make kind of a boundary again to prove if we really have a real, like we call it true Svekofenian ages of 189 something. And we proved, okay, first ages arrived from, I would say, boundary area. You see many spots here. They are on the boundary with Middle Lithuanian domain. And of course, intruded by younger rocks, and we have kind of a mixture. But then we already got some first stages, which were in a perfect fit with real Svicophenian ages. And then we got new ages. We got from metamorphosed felsic intermediate rocks, which underlay Varena iron ore deposit. All these rocks, they're dated dioritic rocks like metamorphosed diorites, metamorphosed granodiorites, or like we call it now orthomyces, and all they produce the same age. I mean, you really have in Eastern Lithuania, you have proper Svicophenian rocks. And then, okay, need of a new map. And for one of our publications, Laurinas produced kind of a first sketch map of a more detailed map. And what is in the base of that map? First of all, we distinguish between like this Middle Lithuania boundary of Middle Lithuania and like true Svicophenian here. And of course, we made more detailed map of Varena, just showing on top of the basement, the uppermost unit. Like if you have granite in your drilling on the top, you show granite. Of course, in a profile, you name all the rocks. That's why in a legend, you have to describe all variety of rock, but we decided on a map, just put the rock which is on the top of drilling. I mean, the uppermost rock. Well, it's kind of approach because you can't show all the maps, you know, in drilling you have different. And of course, for some boundaries, we use some existing old gravity and aeromagnetic maps of Lithuania. Unfortunately, we don't have newer ones, but older ones. And well, I would say it's quite perfect fit. Of course, so many uncertainties. You see some areas which are like of undefined age because you have transitional areas, but I think it works, at least for our purposes, because you have areas, you outline the areas with proper data. With proper data, you mean there you have drillings, and in those drillings, you have dated rocks, you have rocks with the old package of geochemistry and everything else. And then you can extrapolate. Of course, you can show maybe different boundaries in different signs. And then another key area, Varena iron ore deposit, which is very rich deposit, which is where something even maybe reaching to 100 million of tons of iron, and it is very rich iron, and 90% sometimes reaching of magnetite. And it's not so deep as you imagine, because in southeastern Lithuania, crystalline basement, it's only 200 meters deep. I mean, it's really not far from the surface, because, you know, in all other Lithuania, it is deep, but in southern Lithuania, southeastern, it's quite, I would say, shallow. These are profiles of these iron ores, and then what we did, it's a complex. It's a complex. I started in 1993, when I was defending my thesis. My thesis was on Varena iron ore deposit. Of course, at that time, I had just, I would say, sparse data, not the modern one. But well, okay, I presented something like this metasomatic rock scarnation and something. Now many people come to it again because it's really complex and it's worth to study. And I think many people still have to do it and study. And what we distinguished, first thing, we distinguished some currents and some metamorphic currents, we think, of course, driven by fluids. And we distinguished high-grade forsterite spinel pyroxene current, replaced, of course, by serpentine, logopite, amphibole. We have several stages of scarnation, like high-grade scarn, medium-grade, and low-grade scarns. We try to distinguish. We did really proper microstructure work and geochemistry, mineral chemistry, and everything else. And second thing, what we were very lucky at, because you know how difficult to date ores. Really, sometimes it's impossible because we lack proper minerals. But we managed to find badylite, monazite, and zircon, and even in one place, like intergroves of badylite with zircon. And we managed to date, and this is in magnetite. I mean, it's really in a proper ore. It means we really are dating magnetite, at least one enrichment in magnetite. And we got age which a bit surprised us because it was very younger, it 171 million years. It means that we got, this is not age of the Varina itself, but it is age of mineralization. And it's very interesting because, it's, as I said, it's not easy to date mineralization, first of all, and when you have age, now it's much easier to look after the source of iron, first of all, and second, after magmatism, because, if you have scarnation, if you have this type of metasomatic hydrothermal deposit, you have to have igneous rocks related to that. Okay, and then we proceeded, like third case, we proceeded to look after fluids because, to bring a huge amount of iron, and not only iron, other like phosphorus, rare earths, you need fluid. And then this is actually a study by Laurinas again. He started to study in these underlaying rocks, like I mentioned, real Svekofenian granodiorites, we call orthogneisses because they are slightly metamorphosed. Scapolites, because it's a huge scapolitization area, and scapolite is rich in chlorine. And chlorine is a very interesting and very important agent of fluid. Because fluorine, if you have fluorine in present, it's able to leach some minerals from surrounding rocks, to transport them and accumulate. It means, again, fluid composition and changes in fluid temperatures and all other, processes. It's related to metamorphic processes and to later hydrothermal processes. Again, it helps you just to know amount of a fluid, first of all, and how much of actually minerals or like ores can be leached, transported, and again deposited. It means it deals with a scale of a deposit of ore. It's very important because if you don't have outcrops, if you can study structures, again, you go to the micro things, and then you can solve some problems and some which maybe it's much easier when you have it on the surface. And then investigations of metamorphism. Oh, well, I did quite a lot because I started with, first when I went to Lund University, I started with metamorphic rocks. I learned how to use scanning electron microscope, and myself, I did thousands of mineral analysis, and then we used a geothermal barometry at that time. And we produced hundreds, thousands of data, and all this data is published in Skridlaite et al. 2014. All these ages of metamorphic ages, and you see on the left side, you see kind of a summarizing PT path for Western Lithuanian granulites, like starting with speed metamorphic, and you see some several metamorphic overprints. And on the right side, you see very interesting zircons, because here you have igneous zircon, and overgrowth is metamorphic. It means it's very good, you can date metamorphic event. This is really data, and we got a metamorphism of roughly 1.8. It means, again, micro things, but you can solve many problems, because morphology of zircons, they are not produced on ages, but they have many, many important things inside, and you can solve many problems using them. And then, of course, we went further because, especially young people, they're good at using maths and, programs, modeling. And I got like 2 master students working on some PT modeling, and Laurinas himself, he is very good at modeling too. And we produced first models. We used different type of programs like Teriac, and Perplex, and some other, and we got some data, and then we compared with geothermal barometry produced by myself. And then again, we got quite interesting results. And then we used another approach, which is again useful for metamorphism, like monoxide dating, chemical dating by APMA, by this microprobe. It's much easier, it's much cheaper, and you can do it, and they improved it quite a lot. And here you see a monoxide grain, which actually produces 3 different ages. 3 different metamorphic ages. You mean if you choose, and what it's good because you date them in situ. You choose a place like in pig garnet, and then you can date this pig garnet, then you can date second event and third event. Again, it's very good for such thing, this approach. and I really recommend it. And we have very good collaboration with Warsaw University, and they do it, and they are really very experienced in that. They applied new equipment, very high quality one, and then it's really perfect. And now we collaborate with students, like our students do some PT modeling, and they do monocyte ages. That's very good. It doesn't cost anything almost. I mean, and of course, we recognized 4 stages of metamorphism. Here you see all the points. We actually investigated the metamorphic conditions. And we got some, as I said, 4 stages here. First, it's very high, reaching even 900 and at 1.8. And then 173, 168, 162, 158, and then younger ones at 1.5 something, and even younger. But what is interesting, our granulite domain started to disappear because we found out that not all those rocks are granulites. Some rocks are not, and granulites are present only locally. And now we try to just draw just to outline these granulites. And metamorphism is not so uniform because it's overprinted by thermal. If you understand a bit what's like regional, maybe heard in geology, it means implies temperature and pressure, and thermal, it implies mostly temperature. It means we have overprint of the thermal. It means we had many intrusions going on in that place, and it's very difficult to define which one is regional metamorphism because it's mostly overprinted by later stage by thermal metamorphism, and it was revealed by PT by modeling. As I said, students, they got these results. And we are happy and somehow maybe unhappy because it gets more complicated, but it still produces you quite data which fits, like, as I said, monocyte ages. It means we did quite a lot on metamorphism of Lithuania, and of course on Eastern Lithuania too. We're already starting it, but this is mostly in amphibolite facies. We don't have such high temperatures in that part, and of course not much of melting like somebody imagined. There is some, but not in amphibolite facies, and of course not only some rocks could reach melting point in Eastern Lithuania. And another thing what we did, and very happy about, we did some lutetium hafnium on all the dated samples. All dated, we dated like by uranium lead using Norcem and shrimp. And then we, at the University of Montpellier, of course, we have to thank Leonid Shumlansky from the Ukraine and Renaud from Montpellier, who actually helped us a lot. And we got very interesting array, like here. And you see that almost all rocks from Lel and from some rocks from south and southeastern northwestern Lithuania, they all align on the same line. Only exception are clearly hydrothermal or metasomatic skarn zircons, which grew newly, and some chondritic data I will mention a bit later. And all other rocks, actually, they mean that they have the same mantle source. It means we don't have to imagine like microcontinents or many terrains, and actually it proves like idea of many Swedish and Finnish geologists and our, but we have some accretion, southwards yielding accretion. And just you have some older patch, then you have some, of course, it's not just like outlined, it was much more complicated. You have different like structures because you had collision of ceremetia going on. It was a oblique collision. That's why you have one part of it just turned down. And structure is much more complicated, but in general, we can say that all our rocks actually originated from the same mantle, as it's proved by lutetium hafnium data. Again, it's a good kind of a try or well interpretation, and something that helps you a lot. And then I want to present new shrimp data. Now we just got it very recently, 8 samples. And again, they proved that we have real Stepophanian ages in Lel. Now we are going to the east. We are dating rocks more from the eastern part, like dated Metagabro and dated some other interesting rocks. And the most, of course, exciting data, dated some Latvian rocks, Subati or Gneiss. And now we can prove it really belongs to Lel. It's perfect Svepophenian age, it's 189, but we also got some metamorphic ages, some metamorphic overgrowths of 178, 180, and 173. It means 2 overprints. Well, quite interesting to work on. And hopefully maybe in future we will date another rock from Latvia. And then what we really very happy about, we got igneous rocks of 175 something. And why it's important? Because if you remember, I mentioned to you that we got a mineralization of 170 something. And it means now we might maybe have igneous complexes which might be responsible for, first of all, fluids and even iron ore. And this magmatism of 175, it's in gabbros and diorites. It's mafic magmatism. Again, fits very well with Swedish data. They are really, when they heard it, were very happy about this data in Lithuania, because we had metamorphism. We had a lot of more metamorphism overprint of the data, but now we've got real igneous stuff. We expected granites, of course, but we got gabbros and diorites. I call gabbros diorites, but some of them, not those ones, are metamorphosed. But sometimes when you recognize protolith, when you see geochemistry didn't change very much, I call it's easier to call like by real origin. It's much easier. And then here I just put all the data, all available North Sea mushroom data, I mean uranium lead, only uranium lead data, just to show that we have enough data to distinguish between different complexes, different structures, and to go into more details. I mentioned already that Western Lithuanian granulites are disappearing, especially in southern part. We already checked metamorphism, no granulite metamorphism. It means we have to redraw it. And we have to change it, and maybe we just have to put together this Polish structures, because it's very similar. It's like tip 1 or tip even 2. Some rocks of tip 2, it fits very well again, and we have to redraw. We have to do some more detailed maps in that area, but not to detail. And then it's one of our sketch maps I already showed by Laurinas, a small area, and he made it for a slightly bigger area. Again, the same idea. We are putting real data, I mean really dated rocks, and on the drawing boundaries between dated complexes, and of course describing all the rocks which compose this complex. And of course show some kind of lineaments. It's based on geophysics, of course. Geophysics dealt a lot, major structural boundaries, lineaments, and other things. And well, we will try to produce maybe just to the eastern part, to enlarge it and to go a bit further, because we needed why? First of all, because of Varina iron deposit, and second thing, I didn't mention about anorogenic magmatism, like Alvar mentioned. We have plenty of this. And especially in southern Lithuania, like here, you have a huge Kabeliai massif. It's like a continuation of Mazuri from Poland. And it's a very interesting, it's Mesoproterozoic, it's 1.5. And now I have a PhD student who is working on that. We are dating titanites, and we are looking after some mineralizations, because it's very rich in different mineralizations, especially in rare earth elements. We are very happy about that. And some titanite, of course, titanium, and some other, and molybdenum, and some other things. And we are dating, like, now we're recognizing stages of like igneous emplacement, and then by hydrothermal reworking, and looking after mineralizing veins and veinlets and everything else. And as I said, it's maybe continuation of the Mazuri complex. And if you know, in Poland, Mazuri complex, it's a huge complex. It's very rich in mineral resources. It means it enhances, I would say, potential of this region, because it's not very deep, as I said. Actually, it's even reaching under 100 meters to crystalline basement in some places. Well, and what I want just to share our experience recommendations, because of course, to map crystalline basement is really kind of a challenge. And you have to find some kind of approach. As I said, first of all, you have to create a model, because otherwise you just did, randomly everything, and you get a mess. And then you choose key areas just to justify your model, which are very important, where you can solve some problems. And then you just analyze and study those key areas very carefully by means of uranium lead dating, zircons monazite, shrim, northsim. I mean, really not just this conventional, because they dissolve zircons. Our zircons are too complex. Use this point analysis like shrimp and northsim. Of course, samarium, neodymium, rubidium, strontium is very important, as I show, for assigning to the same series, so, you know, finding some complexes. Lutetium, hafnium, again, for crystalline evolution. If you see, is the same source or different. Of course, 3F spider diagrams, microstructure, mineral chemistry, and PT modeling. Now it's easy. It's a lot of different models. You just had mineral data, had whole rock chemistry, and you can produce a lot of different type of diagrams and choose which ones are really reliable one. And of course, then you produce sketch maps for these like key areas. And of course, then you can extrapolate. Then you can use geophysics, and then you can extrapolate real data. But again, you have a lot of problems, like which boundaries are really reliable, which ones are like not also reliable. Maybe you have to distinguish between them. And of course, you have transitional area. You have no data on that. We have to, well, but it's kind of like technical problems. Maybe we have to solve all together. And of course, as I said, extrapolate, and then probably we will finish in some years, but mapping it takes, because first of all, you have to collect data. I wouldn't advise just to draw maps without a proper collection of data. You have to be sure you really have that rock in that particular place. And it proves, as I said, by isotopes. Isotopes are very important because we have small pieces. And you know, this isotopic and microstructure approach, it helps because you don't need much of material. And you know, dating rocks, like nowadays, again, you need small pieces. You don't have, you know, to dissolve huge piles of drill core. It means it's really helpful. And as I said, you can solve really serious problems just on those small pieces. Okay, thank you for attention.